Hello friends, this is part 4 of 6th semester nuclear and particle physics paper, DAC 1 of 2023, Dibrugarh University. If you want to follow me on Insta, this is my Insta ID, OJHALAKHYAJIT123. This is my Insta ID. And before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you. So now let's start. So here you see, this is the first question, question number 5a. We have already solved up to question number 4. Discuss Rutherford scattering in a nucleus. So here is the answer. So you have already studied in senior secondary level that Rutherford took a very ultra thin gold foil through which alpha particles are projected to strike on this gold foil, and it was observed that most of the alpha particle passed through this and deviated by a very small angle, right? And very few particles scattered at an angle of 90 degree, and very less number of particles are rebounded, making 180 degree, right? That number is very, very less compared to this 90 degree deviation and those particles, number of particles passing through it with a very small deviation. Okay, so that was his experiment. So he made the conclusion that he proposed that inside the atom, the positive and because alpha particle is positively charged, so to deviate it, there must be a positive positive charge, right? So almost the whole positive charge of an atom are concentrated at a central region and concentrated in a very small central region that is called nucleus. Okay, and you see, suppose a heavy nucleus with charge Ze. So why Z is the number of proton, and charge of each proton is equal to the charge of electron. Charge of proton and charge of electron same but opposite in nature, so one is positive, other is negative. So positive E means charge of proton, negative E means charge of electron. Okay, so now you see, this is the charge of a nucleus at rest. Then alpha particle is projected with of charge 2e would describe under the central force, inverse square force, law of repulsion, according to this law, that F is equal to K Q1 Q2 by R square. Hope you know this law. Under this force of repulsion, because alpha particle is positively charged and the nucleus is also positively charged, nucleus is at this point, which is another foci of this hyperbola. Hyperbola has two foci, right? So now you see, this alpha particle will describe this hyperbola, this part, and from the vertex, this nucleus is at K, is at a distance of R, and from the equation of hyperbola we used to get this relation where E is the eccentricity is this is the eccentricity, OK is the eccentricity, and from this triangle we get this relation sin theta is equal to B by epsilon. And if we use this relation here, then we get this relation, right? And if you simplify this using trigonometric identity, then you're supposed to get R is equal to B cot theta by 2. That's what we're gonna get. So this is suppose equation number 1. Now here you see, so hope you know this meaning of asymptote. The line that towards which a curve approaches towards the line but never intersect. Okay, they intersect at infinity, you can consider that way. So here we have two asymptote. This is along which this alpha particle is coming, and after after repulsion due to this positively charged nucleus, it going back along this direction. Okay, right? And an angle between these two asymptote is phi. Okay, hope you have understood this. So now, sorry, okay, so here I have mentioned the angle phi. Okay, so capital M is the mass of the alpha particle I have taken. Then by conservation of energy, so here this is the kinetic energy of this alpha particle, where v naught is the velocity of the alpha particle, right? Actually, velocity of the alpha particle is v when it comes closer to that nucleus, at k, nucleus at k. So let me copy this diagram and let me go to the next slide. Okay, let me copy this diagram as well. Okay, here is the diagram. You can see, in order to explain, I have copied this. Okay, so here you see, this is the parabola. Okay, hyperbola. Okay, now you see this alpha particle is going with velocity v. When it reaches the point A, vertex A, due to the repulsion, its velocity becomes, suppose, v naught. Okay, it changed, velocity changed. So at this, it must have a potential energy which is given by this, the potential energy. We have a charge q, and at a distance r, suppose another charge small q is kept. Then potential energy due to this system of charges will be is given by v is equal to k q small q by r, right? So here k is nothing but this 1 by 4 pi epsilon naught, right? So here capital Q is Z and small e is the small q here, right? Hope you have understood this, that small e is the charge of the alpha particle and Z is the charge of the nucleus, right? So let me clean these things. Okay, so now you see, so kinetic energy plus potential energy, that must be equal to the kinetic energy of the alpha particle before it reaches the point A, because total energy is conserved. So the energy of the alpha particle is purely kinetic when it before it goes to a point close to the nucleus. Then when it comes under the influence of the nucleus, then it must have there must be a change in kinetic energy, and it must have potential energy as well at this point A. So here potential energy, kinetic energy is equal to the total energy it had before it comes to the point where this ZE has influence. Okay, so here total energy was half mv square, right? When it reaches the point when it reaches the point A, it has kinetic energy half m v naught square plus also have potential energy, right? So hope you have understood this. So now you see, if we simplify these things, these equations, so we end up getting this equation, right? So here you see, we have replaced this term, we have, sorry, not this one, we have replaced this ZE by this by a constant k. Okay, and we have got this relation. Okay, now you see, let me go to the next slide. By conservation of angular momentum, so now let me go back to the diagram. Okay, so here you see, when the alpha particle is at A, then angular momentum of this particle about this nucleus k, here we have the nucleus Z, right? So that will be given by, if its momentum is a linear momentum is suppose m into v, then at this point, okay, at this point when it reaches A, its velocity becomes v naught, right? So linear momentum must be m into v naught, and the distance from this the point where we have nucleus to, in order to find the angular momentum about this point k, we have to multiply this distance r, right? That's how we get angular momentum. Similarly, when it reaches this point, suppose, and at this point here you see the distance to this asymptote is b, so here we get the angular momentum when its velocity is suppose its velocity is v now, so mv. Now that now we're gonna take this distance b, right? And when the alpha particle is at a, then we have to take the distance to this tangent, to this asymptote. Okay, so hope you have understood this. So we have got, by the conservation of angular momentum, this relation. Okay, then we're gonna put the then from here we're gonna obtain v naught by v, right? And then we have used equation number 1 in order to put the value of this. So here you see in equation number 1, this is the equation number. Where is equation number 1? Here. So b by r, we can obtain b by r from this relation. So we have got this, right, using equation number 1. So then what we can do, squaring both sides, we get this relation. And if you simplify this relation, then you must get this, because sine square is nothing but 1 minus cos square theta, and which can be written as 1 plus cos theta into 1 minus cos theta. Then 1 plus cos theta cancels this square, then we have got this relation. Hope you know this simple simplifications, right? So then if you simplify this, then what we're gonna have, let me check. Okay, so using equation number 2, what is equation number 2? So this equation, if we use this equation instead of this, then this value is replaced by this term. Then if you simplify further, then you're gonna get this relation. Okay, so this is all about the Rutherford scattering. Now this tan theta can be replaced by cos phi by 2. Sorry, this should be cot, not cos. This is supposed to be cot. Okay, so here you see, because you see from the diagram, from this diagram, you can see this is phi, right? This is phi and this is theta. Okay, now you see, let me draw the diagram again here. Sorry, this was the part, and asymptote, this is another asymptote. This angle is, if this angle is theta, this must be also theta, and this is phi. So this angle is 180 degrees, so that is pi. So we can write from the diagram, you can see that pi is equal to obviously theta plus phi plus theta, which means phi is equal to this pi minus 2 theta. So then from here we can obtain theta. Theta will be equal to theta will be equal to what we're gonna have, that pi by 2 minus pi by 2. Okay, so if you replace this theta with pi by 2 minus pi by 2, then applying ASTC rule, we're gonna get this relation. Okay, so hope you have understood this. So now let's move on to the next question. Now we're gonna answer this question 5b, derive an expression for Q value of nuclear reaction. So let's derive this equation. So here is the answer. Now let me explain this. Now we have this diagram is necessary. We have a target nucleus. This is suppose capital MX, and we have this projected particle, okay, of mass small mx. Okay, and it is moving with velocity vx, and it is at rest. This target is at rest, right? Then it collide with this, and due to nuclear reaction, so we have a daughter nuclei, which is this one. It is of mass capital My. This is of mass capital My, and a scattered particle, which is suppose this will be small my. This will be small my, suppose, right? And velocity of this capital My is suppose v1y, and velocity of this small my is suppose v2y. We have considered that way, right? Then the angle of this scattered particle is suppose theta, and that of phi, the daughter nuclei is suppose phi. We have taken that way. Then by the law of conservation of linear momentum, now you see linear momentum of this particle before collision is mx vx. That is what we have written here before collision, and as it is rest, so its linear momentum is 0. So mx vx plus 0 again, total momentum before collision mx vx, right? Then total momentum after collision along this direction, you can see, because this particle is moving in this direction, and we have no any other linear momentum along y-axis. We have only linear momentum along x-axis. So if the velocity, this velocity is in this direction, then in this direction we're going to have this component v2y cos theta, and velocity component of this velocity vy1 along x-axis, it will be vy1 cos phi, right? So hope you have the idea of vector component. If this is v and this angle is theta, then it is v cos theta, and this is v sin theta, right? This component is sin theta. Now you see here we're gonna get sine component also along this direction. Along this direction, this two will be will not be taken. We're gonna consider the along x-axis only. We are taking along x-axis only. So when you take along y-axis, now if you consider the it along y-axis, then what we will get? Considering along x-axis, we have got this equation. Then if you simplify this, then you're gonna get my vy1 cos phi and mx vx minus my v2y cos theta, right? Because you see, momentum before collision, total momentum before collision is mx vx. It was at rest, right? Before collision. After collision, one nucleus is going in this direction with this velocity, so its momentum will be my v1y, but this component, this x component, will be capital My v1y. This is the momentum component, x component of the momentum of this particle, and the projected particle, scattered particle, its momentum should be my v2y, but in x direction it's supposed to be my v2y cos theta, right? So along x-axis, this is the total momentum, is the sum of these two momentum along x-axis after collision, and before collision is this, right? So now you see, when we consider the when we take the y-axis, this y-axis, so then what happens? Initially, you see this particle is moving along x-axis only, so we have no initial momentum before collision along y-axis, so that's why we have taken as 0. Then after collision, we have this my sin my v2y sin theta. Similarly, along this, this is the capital my v1y cos phi, and along in this direction, it will be my v1y, that will be sin phi, right? So, but this is positive x-axis, this is negative x-axis, that's why we have used here minus sign. And if you simplify this, then you're gonna get this equation number 2, right? So now let me go to the next slide. So here you see squaring equation number 1 and 2, then adding, squaring these two equations and adding these two equations. Is after squaring these equations, we have added these two equations, then we have got this relation, right? So you can check yourself. If you square this both side of this equation, okay, then if you expand this using a minus b whole square formula, then if you add these two equations, if you add the two results after squaring, then you're gonna get this results, right? So I don't think I need to show all this simplification. So now you see this my is capital My is written as my into my. Then we have multiplied 2 here. Then again we have multiplied 1 by 2, because 2 cancels. My square. Again we're gonna get this term. So why we have written this way? Because you see now it becomes kinetic energy of this particle. Here you see kinetic energy. Okay, kinetic energy of this one will be given by this my. Vy1 is moving with this velocity. This my is moving with this velocity v1y. So its kinetic energy should be half capital My v1y square. Right? We know that kinetic energy is given by half mv square. Using this formula, we have got this. Now here you see we have taken the kinetic energy of this particle. We have taken. Let me clean these things. So this is capital My. It is moving with this. Its kinetic energy should be My y1y square. So let's represent this kinetic energy by k1y. Similarly, we can find the kinetic energy of this scattered particle, which is suppose k2y, which is going to be equal to half v2y square. And its kinetic energy is 0 because it is at rest initially. So its kinetic energy should be 0, and its kinetic energy is kx is equal to mx vx square. Not only that, we should put a half here. Okay, similarly, okay, that's okay. So this is the total kinetic energy before collision and total kinetic energy after collision, this one plus this one, right? Now you see if we use this kinetic energy, similarly we can express this as 2 into mx, half mx. If you multiply these two cancels, mx square. So again here we're going to replace this by kx, kinetic energy of the particle of mass mx. Similarly we can replace this by k2y, right, kinetic energy. So here you see this term can be written this way, putting square root, then again whole square. Then we can simplify this way, okay, in order to bring the kinetic energy term. Okay, so hope you have understood this. So this is replaced by kx, this is replaced by k2y. Okay, so we have got this relation. Now you see one more thing, this 2 into 2, that's 4. Square root of 4 is 2. Then this 2 into this 2 becomes 4 here. Okay, that's it. Hope you have understood this. So I have mentioned the kinetic energy terms here, and from here we can obtain the kinetic energy k1y is equal to this. Okay, now you see, let me go to the next slide. Here you can see we know that Q value of a nuclear reaction is given by this. That means you see, suppose this is a parent nuclei and it is targeted by a particle. Okay, so initially it must have kinetic energy. Suppose let it be kx, then it is it gives out from here we have a daughter nuclei with kinetic energy k1y and a scattered particle with kinetic energy k2y. Okay, so now you can see, then you will see that this total kinetic energy before collision and after collision not equal. Okay, are not equal. There will be a difference in kinetic energy, which is the Q value of the nuclear reaction. So total kinetic energy after collision is this one minus the total the kinetic energy before collision gives the Q value. Okay, so now we have used this equation number 4 in equation number 3. From this equation number 4 we can obtain k1y is equal to Q minus 2y plus kx. Okay, so we have used this expression here. Okay, so then we have got this relation. Okay, then if you simplify this, then you're gonna get Q is equal to this. Then you can take kx common. Okay, similarly from this two you can, sorry, not this one, from this two you can take k2y common, and taking this we have got this relation. Okay, so this is the expression for Q value, or Q equation. This is also named as Q equation, right? So now let's answer the next question. So here you see, so we have a numerical here. So we're gonna use the formula now we have derived for 5b. We're gonna use this equation here to solve this problem C. Okay, so here you see a alpha particle is this, right, of kinetic energy 7.7 MeV. It targets a nucleus of nitrogen 14 here, which atomic number 7, and daughter nuclei is N17. And so let me explain it properly. So what happens here, this alpha particles targets this N14 7 and a nucleus, this N8 17, and a particle H1 is scattered, and this makes an angle 90 degree with this direction of alpha beam. Okay, so here our theta is 90 degree, right? So now let me take a new slide. Here you can see. Okay, here let us solve this. Okay, now you see, as mass of this nuclei are not given in the question, so we're gonna take the mass number of this nuclei here. Okay, so as alpha particle is nothing but this nuclei represented by this nuclei, actually not helium. A helium atom also contain electrons, but when you say alpha particle, it should not have electron. But as you know, the number of protons and number of neutrons that helium nuclei has, the same thing that alpha particle has, right? So that's why we used to write that way. So mass of that alpha particle, we're gonna take this as 4 into if we write in MeV, so we know that one atomic mass is equal to 931.5 MeV. So we have to multiply 931.5 MeV, right? So mass of N 14, that's going to be 14 into 931.5 MeV, and mass of this daughter nuclei, that is we're gonna take 17 into 931.5 MeV, right? Then mass of this H1 particle, that's gonna be 1 into 931.5 MeV, right? And what we have theta is equal to 90 degree here. So here we're going to use this relation that we have just derived. So let me copy this relation and let me go to the next slide. So here we're going to use this relation. Okay, so in this case this is the small mx here. This small mx is the mass of the alpha particle, that particle which strikes the target nuclei. Target nuclei is capital Mx, and daughter nuclei is capital My, mass of the daughter nuclei. And the kinetic energy of this particle is also given, but mass of this particle is small My, and mass of this particle is scattered kinetic energy of this scattered particle is given. The kinetic energy of this is given, that in the question it is given 4.44 MeV. So for us this is going to be the K2Y, right? So if we use these values here, then what we're going to get? So I haven't multiplied this too, because you see these numbers will be cancelled out. Let me show you how. Okay, so here you see, put the values here, then what you're going to get, 4 into 9 931.5 by my is nothing but your 17 into 931.5 minus 1, kx is your 7.7 MeV. Okay, so kx is here, this is the kx, 7.7 kinetic energy of this alpha particle. Okay, kinetic energy of this alpha particle. So kinetic energy of alpha particle is kx, yeah, 7.7 MeV, right? The particle which strikes the target. Okay, so plus then we're gonna have small my is this scattered particle 1 into 931.5 by the daughter nuclei is this 17 into 931.5 plus 1 into K2y is the kinetic energy of the scattered particle, that is 4.44, and this term will be 0 because here you see we have theta 90, that the angle made by this scattered particle with this alpha beam, direction of alpha beam, this direction of this alpha beam is 90 degree, and cos 90 is 0, so that's why this term going to be equal to 0, since cos 90 is 0, right? So here we're gonna get 0 minus 0, right? So if you use calculator, and I have used here calculator, and using calculator we have got this value approximately minus 1.2 MeV, minus 1.2 MeV approximately. So this is your answer. Okay, so hope you have understood this. So there is another question, either you have to solve this problem or you have to write this answer. What was that? This is 5C, or difference between the direct reaction and compound nucleus reaction. So here is the difference. Okay, so let me show you where I have written. Okay,